to be here again. Thank you very much for very kind introductions, Eni-san. Today, I'd like to just talk about the multi-scale modeling of the structural concrete. But this is just so. It used to be my hobby. We have to think about the life, remaining life of the structure. This was already used. When we construct a new structure from now on, then this is experimental facts without any ASR damage. This is a number of cycles and also deflections. Without any damage, this is a prediction. This experiment. It is about 1 or 2 million cycles structure fail. But if the ASR occur, life is around that 10 million cycles. Like this. So this is true because damage is introduced, but the volume is expanding. But the reinforcing bars exist. Therefore, counter compression force is applied to the slabs. Therefore, permanent stress level is higher, but amplitudes of the stress caused by the traffic become small. Fatigue problem is mostly governed by the amplitudes. Therefore, so much damage, but because of the presence of the reinforcing bars, life is prolonged. Another thing is that in case of the normal concrete, and if we have a water on the structures, I said that life is shortened about 100 times or 1,000 times shortened. But when we put the water, Professor Iwaki of Nihon University put the water of ASR damaged structures and applied load, life was not shortened. With and without water, life is not change. Very simple. Because of a lot of cracks, water comes, but very easily water is drainage. Therefore, pressure of the water does not rise. Therefore, damaged concrete have a high performance against this one. Therefore, very unfortunately, Japanese government, when we have ASR, oh my God, so injecting the chemicals and stopping the traffic, so much money, so much time. Then, after that, the performance is lower. But if we don't do anything, performance is becoming longer, like this, right? Then with this one, so some multi-scale models has been used for that type of problem, some damage. But please understand for corrosions, when the corrosion occurred, the life is shortened. But big problem is that when the corrosion occur in the bottom reinforcing bars, we have a top reinforcing bars and bottom reinforcing bars. When we have corrosions in the bottom reinforcing bars, life is not changed. Nothing almost. But if the corrosion occur on the top reinforcing bars, so much damage. Right? Maybe you understand that. Maybe bending compression zone is damaged by corrosions. But the bottom cracks, bottom reinforcing bars have some cracking. But I think you know that in bending, already cracks. Therefore, even though the cracks, concrete in the tension zone will be damaged, structure performance will not change like this. But the very ironic thing is that bottom reinforcing bars corrosion can be seen by naked eyes. Oh my God! But the top layers are covered by asphalt. Cannot. Therefore, in the past, many engineers found some corrosion on the bottom reinforcing bars. Oh my God! They repaired, but no way, no contributions. Like that, it happens. Therefore, this is a combination of material science, corrosions, and structural engineering. Well, excuse me. But I think there is one funny thing. This is a local things of the Japan. The railway engineers, bridge engineers, when we open these informations, these engineers contact us. Please, Professor Maekawa, that is science, it's okay, but please, publish this report in English, not in Japanese. Oh, it's all right, but anyway, but he said that. So by having some ASR damage, structural performance is upgraded compared to the initial situations. It's okay? Then when we apply the Japanese national law very strictly, in the next year, these bridge owners have to pay more tax, right? When you, in Japan, when we built our house, right? Next year, we have to pay tax. When the first story, when we have some other second story, then next year, this is the creations of new values. Therefore, toward the new values, we have to pay tax, right? But in this case, performance is upgraded. So the value is upgraded. Ministry of Finance, if the Ministry of Finance know this one, they try to apply the tax, right? It's a big problem. Therefore, they said that. But I said to them, no. Ministers, government officials of the Ministry of Finance maybe cannot understand this one, right? Then, but anyway, they worry about that. Therefore, they said that when this report will be published in English, you know that in Japan, language barrier is so high. Therefore, non-engineering people do not read English-based informations. That's all right. Almost several years have passed. They do not pay so much tax. That's all right. Maybe. Anyway, it's the results. So, so we have some other things, but I would like to conclude my talk about this effect deflections. Maybe bridges, long-span bridges. But I think some long-span bridges more than 100-meter span lengths in the world suffering from the excessive deflections. So about 10 years ago, there is a very famous international conference organized about creep and shrinkage. You know the creep and shrinkage. So some engineers of Japanese companies reported that the periodical inspection data of the deflections, like this. Then this one is design code predictions. About 30 years after construction, maybe about 3 centimeter deflections at the center span, but in reality, more about 4 times, 5 times large. But up to the 5 or 6 years, almost the same. But after that, this is also the case. So deflection is going down. We don't know what happens in the next 50, 40 years. This was reported by the bridge engineers. But at that time, he himself supposed that this is due to the bad constructions. Because of bad construction, the deflection is going down. But anyway, he's very much honest. Therefore, he published this one. But after these conferences, I know that he was surrounded by many bridge engineers from many countries. France engineers, German engineers. They said that, oh my God, I have the same experiences. Because many people suppose that it must be due to the bad constructions. Then they hide this information. Because this is a shame. But I think maybe this is not caused by the bad construction. Maybe caused by the incorrect, bad design code. Maybe. Something wrong. This is common things. Then Professor Bajans of the Northwestern University collected these many engineers. And it was found around 100 bridges data was collected. This is the time after construction. This is the deflection normalized by the initial. You can see that this dot line is data, logarithmic scale, there is no terminations of deflections. 70, 50, 70, 100 bridges of long span bridges, deflection is going, even 50 years, 60 years. And so some bridges collapse. The Republic of Palau without any applied law. Then many engineers suppose that. So these are based upon the creep and shrinkage design method. Maybe there must be some big mistake. But middle span bridges, there is no problems. Almost okay predictions, and the design predictions and reality are close to each other. But hollow types, long span bridges, for this case, big deflections. Then, anyway, but I think one colleague, Professor Chijiwa of the Tokyo Institute of Technology, applied the new multi-scale modelings. Surprisingly, this long excessive deflection was predicted. But the reason is very simple. Okay, big structures, big long structures, some top slab thickness is about 20 centimeters or so, but the bottom slabs, bottom flange is about 1 meter sometimes. When the middle span, maybe not so much, but the long spans, therefore, size of the top and bottom slabs are different so much. Well, okay, so you understand that. When this is exposed to the natural environment, so top slabs, because of the thin slabs, when we wait 3 or 4 years, center of the slabs is almost equilibrated with the ambient relative humidity. But in case of the 1 meter flange, right, in this case, in order to have a drying at the center of this one, it takes about 50 or 70 years. Right, because the speed of the clock of the materials is quite different. Therefore, this flange will be shrinking when we wait about 50 or 60 years. But the top slabs shrinkage really terminated just several years. Because of this, you see, so curvature is introduced. And also, double integral of curvature becomes the deflections. So huge deflection comes like this. Therefore, PC, pressing force, is not reduced, right? Because overall, shrinkage, creep is small, but the difference of the top and bottom is large. Then this one will change. But unfortunately, in designing the long span bridges, drying shrinkage data of 1 meter thickness of concrete not used. Well, generally speaking, we can measure the drying shrinkage of concrete as a material properties around 10 centimeter, right? Then when we wait about 2 years or so, almost shrinkage stop, right? Therefore, this data should be used to design this one. But when we have 1 meter, okay, let us have some specimen of 1 meter, 4 meter. Let us measure the shrinkage. Okay, you can wait 50 years. You can have a shrinkage data. This data should be used for this bottom one, right? If so, deflection can be obtained. But you see, are you going to wait 50 years to obtain the shrinkage of the big size? Then nowadays, these multi-scale modelings can handle the loss of the water, migrations, and corresponding mechanics and so on. Then we also change the design code practice. Maybe I skips. Then long span bridges, deflection can be nicely simulated. But just after the construction, about 3 or 4 years after construction, design code and the current design code, all design code and real structures deflection are almost okay. You understand, right? Just few years after construction, top slab, bottom slab, more or less wet. More or less wet. But when we wait about 20, 30, 40 years, drying conditions of each part is becoming different. Therefore, the differential deformations may create some deflections. Then this is one thing. So, okay, I'm going to just skip this one. Excuse me, but anyway, I'm going to skip this. Then, with this one, some question comes. This is a story of the bridges. How about the buildings, right? Buildings. So when we have different shrinkage according to the place by place, some impact may come to the normal buildings made by concrete. But it's very difficult to get this data. But one report was coming. This axis is the year after the constructions. And this axis is a natural frequency ratio. Natural frequency ratio is that when we introduce some small vibrations, some frequency is obtained. This is related to the stiffness of the structures. Therefore, when we have a 20% down of the natural frequency of the structures, it means that about 50% of the stiffness is reduced, because the stiffness, root of the stiffness is proportional to this one. Therefore, 80% or 70% down, it means that structural stiffness is about 50% down. Okay. So then some people said that, so this is not reality. So, but this data comes from the Research Institute of the Building in Tsukuba areas, Building Research Institute. Therefore, we have to accept. And another thing is that about 6 years ago, the earthquake comes to the Japan's. Northern part of Japan are so much suffering from this one, but big waves come to the city of Tokyo and Yokohama. There are many buildings. And also recently, they put some sort of the acceleration sensor. Therefore, about nearly 100 buildings data was measured. Very surprisingly, of course, just after the opening of the building, they measured the natural frequency by using some devices. But several years later, big earthquake came. The many buildings are shaken. Then this sensor found these drops of the natural frequency. Generally speaking, about 5 or 6 years after construction of reinforced concrete, stiffness of the building is becoming 50%, almost down. Then it was found that this is a real scale experiment. Sometimes earthquake will give us very important information because real scale. Then, but unfortunately for nuclear power plants, these are constructed with very thick walls, almost 1.5 to 2 meter big walls. Therefore, it takes so many years for having some drying inside this. Therefore, this is pictures of nuclear power plants. About 30 years, just 10% low. But anyway, when we wait another 100 years, the same thing happens. Then nowadays, you know that so nuclear power plant in Japan are now shut down. In order to resume this power plant, many mechanical engineers investigate the natural frequency. And also when the natural frequency would be different from the initial one, so something happened. Then if the civil engineers could not answer these questions, no power plant are not allowed to be open again. Nowadays, very surprisingly, the new multi-scale modelings have been used for that. So this can be captured like this. But this is now the situation where I have them. But anyway, for the seismic safety issues, there is no problems. Then now, so situation is changing. Society's requirement is changing. Therefore, I want to say that about 25 years, they said that this is not good. This is no contribution to the practical problems. But nowadays, many cities, or its performance of the existing structures are required. checking is required. Now this is now the change of the background. The same things for the This is the real scale 7-story reinforced concrete buildings. And this was shaped by using the same ground motions of the earthquake in 1995. But in simulating these structural behaviors, we could not understand that situations are, how to say, this one is deflections of XY directions, very complex deflections. When we do not consider the water loss from the members, behavior is that's just blue color, very small. But when we consider the drying of the structural members of the buildings, response is this one, like this. Therefore, in order to simulate the earthquake resistance or the earthquake response of these buildings, so dryings or water loss impact must be considered. Otherwise, the real shaking behavior cannot be captured. Then this was now a few years ago published. But so I encounter big difficulty, right? Because in the past, Japanese buildings are designed based on the design code without any considerations of the drawings. At the same time, architecture engineers said that computer simulation is very much successful compared with the reality. But past successful simulation never considered the impact of the water loss. If this one would be accepted, so many papers in the past decades through the structural engineers for earthquake engineering will be, denied. Yes. Therefore, some engineers, some students encounter big difficulty, a lot of attack. If this one would be accepted, so many professors tell a lie. Yeah, but it can happen. Then finally, I came to know that. One professor from Beijing professor said, "Oh, Maekawa-san, in fact, when we do not consider this type of things, computer simulation never simulate the reality. Therefore, all companies' engineers intentionally reduce the stiffness of the structures about 50%. Then, as a result, so behavior can be captured. But this was not written in technical papers. Yeah, I didn't know that. But I think this is not fair, indeed. Not fair. They said that this is successful, but they tell lies, academically speaking. Therefore, please keep in mind, when you encounter some difference between your thinking and results, sometimes, if this one would be really against the popular opinions, yeah, sometimes you can be true like this. But anyway, also, this is a case. But he said that this is not a secret. Everybody do like this. But this is not internationally known by that. Therefore, I could run. But anyway, when we have some shrinkage, some internal stress, already introduce the structures. And very early cracking can occur like this. Anyhow, now this is now the current situation. Almost time has come. Therefore, I would like to stop my talks. Also, But anyway, still, so each part is now under development. Therefore, this is some intermediate reports. So thank you very much for your kind attention. I will just conclude my talk.